So let's start next canonical forms, triangular form. There are a few canonical forms that we are going to consider in this text, and the triangular form is the first one of them. So let us start our discussion by considering an n-dimensional vector space. Let V be an n-dimensional vector space over some field F. We are next going to define a binary relation in the algebra A of V. That means this relation is going to relate two linear transformations on V or two linear operators on V. And this is the definition. And this relation is called similarity. Two linear operators. In the text, it says two linear transformations. But I use the word operator when both the spaces are the same. In other words, when we consider a linear transformation from a vector space into itself, then such transformations particularly are called operators. Okay, so two linear operators S and T, which are elements in this algebra of operators, are called similar if there exists an invertible operator C in the algebra such that T is equal to CS C inverse. Actually, you can write C inverse CS also, nothing essentially changes. Okay, so when such an invertible operator C exists such that T is CS C inverse, then we say that S and T are similar. Now we already know that this operator algebra is isomorphic to the matrix algebra Fn, consisting of all the n by n matrices whose entries are coming from the field F. So, using this, we can similarly define similarity of two elements in Fn, that is two n by n matrices, like this. Similarly, two matrices A and B in Fn are said to be similar if there exists an n by n invertible matrix. In other words, there exists an invertible matrix C in Fn such that B is equal to CA C inverse. Do not confuse this C with this C. Okay, that is an operator and this is a matrix. For some reason, the author has simply chosen to name both of them C. You can give some other name also, say D. Okay. Now, this relation, it turns out, is an equivalence relation on this algebra. In fact, that's very easy to see. Let's just go through the details. Similarity is an equivalence relation on A of V. How shall we prove this? Well, we have to show the three things, namely that the relation is reflexive, it is symmetric, and it is transitive. So let us take any three elements. Let S, T, and U be any three elements in our algebra. Since S is equal to 1S 1 inverse, where 1 is the identity operator on V. Well, we know the identity operator on V is just the identity function on V, which turns out to be the unit element of this algebra. And that is, of course, it's known that it is invertible with itself as its inverse. And when you take the product of 1 and any element of it, because it's the unit element, so you get the element back. So from this equation, we get the fact that S is similar to itself. S is similar to itself. This proves that similarity, this binary relation, is reflexive because every element is similar to itself, it's related to itself. Next, let S and T be similar. Then S is equal to, well, okay, we should not change the definitions simply carelessly like this. We should write exactly how it is defined. And once we prove that the relation is an equivalence relation, then we can use it in any way we want. So that's why I should write T equal to CS C inverse for some invertible element C in the algebra. But then S is equal to C inverse T C inverse inverse. We know that for an invertible element C, its inverse C inverse is also an invertible element. So using that fact, we can write T is equal to C inverse S C inverse inverse, and obviously C inverse is also an element of this algebra, and that's why T and S are also similar. Okay, so that means our relation of similarity is symmetric. And next we have transitivity. Next, let S and T be similar and T and U be similar. Then we will have two things, two equations. T is equal to C1S, C1 inverse, and U is equal to C2T, C2 inverse for some invertible elements C1 and C2 in our algebra. Okay. Now, start with the second equation. U is equal to C2T, C2 inverse. In place of T, you can substitute this. So you get C1S, C1 inverse, C2 inverse. But due to associativity of multiplication, we can take C2 and C1 together. S, on this side we have C1 inverse, C2 inverse. But this is just C2 C1 S, and this one is the inverse of C2 C1. You remember this fact from group theory, because after all the invertible elements in A of V form a group under multiplication. In that group, if you calculate the inverse of C2 C1, it's the same as C1 inverse, C2 inverse. The order changes. Okay, so we now have this where, of course, because C1 and C2 are invertible elements, so is C2 C1. Again, because of the fact that the invertible elements form a group under multiplication in this algebra, where you can mention that fact, where C2 C1 in A of V is invertible. So, S and U are also similar. Thus, similarity is an equivalence relation on this algebra. Looking at the form of this relation, form of the relation means its definition. It seems like similarity is almost like the conjugacy relation in a group. But beware, it's not exactly conjugacy, because all the elements in the algebra do not form a group under multiplication. Only the invertible elements do. Here, however, our relation relates non-invertible elements as well. Any two operators. Okay, they may be related, may not be related, that's a different thing, but they come under the scope of our relation. Oh, okay. So that is why this similarity relation, although it looks like conjugacy from group theory, is not, they are not the same thing. Alright. Now because we have proved that this is an equivalence relation, it will partition this algebra into disjoint equivalence classes. And these classes have names. The equivalence class of an element in AV, that means the equivalence class of an operator, the equivalence class where the operator lies, is called its similarity class. Okay, just like for the conjugacy relation in a group, we call the equivalence classes conjugate classes or conjugacy classes. Here, the equivalence classes are called similarity classes. Okay, now comes a natural question. Suppose two operators are given to us. How shall we decide if they are similar or not? Say we are given S and T in A of P. How will you decide if they are similar or if they are not similar? What will you do? Well, one way of thinking of this problem is like this. This is your entire A of V. In this, you have the operator S, for example, as an element. Now, S has its own similarity class. The subset here, which you see, consists of precisely those operators that are all similar to S and hence similar to one another. Any element that lies outside of this subset is not similar with S. So, what you do, you scan this similarity class of S fully and look for the operator T here. If you find T there somewhere, then S and T are similar. But if T lies here, then S and T are not similar. Now, of course, this is not computationally feasible. This is because the similarity class of S may be really large and even may be infinite. Okay, so you cannot, of course, look for every operator and see whether it is T or not. It's just a dull approach and it won't lead you anywhere. A better approach is this. Again, let me draw a diagram because that way we can see everything in front of our eyes. Suppose this is A of V and these are the similarity classes. Okay, they partition A of V into disjoint non-empty sets whose union is A of V. That's what partitions are. So what we do, we identify some kind of landmark, some elements in each similarity class as a distinguished element. Okay, these are landmarks, so that when you are in a similarity class, say here in this class, and there you are sitting near a given element, then there is a way of going from that element to the landmark of that class. If you, for example, are in some other similarity class and are looking at some element from that similarity class, there is a way of going from that to the landmark. All right? And we will prove the existence of these landmarks. And these landmarks, of course, they are after all going to be just elements in A of V. That means they are going to be linear operators. However, we will prove that such operators exist whose matrices under some, with respect to some given basis for V, are particularly simple. Those matrices are going to, for example, say these are the landmarks. Okay, by some means you have identified these landmarks, and these landmarks are such linear operators that if you find the matrices of these operators with respect to some special basis for V, then those matrices take some specific form, which is something special and something simple also. It's not just any matrix. Okay, so that's what we will do. And those matrices will be called canonical forms. So to answer the question of whether two given operators are similar or not, what you do, you compute their canonical forms. If the canonical forms are the same matrix, then they are similar, otherwise not. Now there are many canonical forms, but in this text we are going to see only 3. One of those 3 is, of course, this triangular form. But besides that, we also have the Jordan form. And lastly, we also have, in this text, the rational canonical form. So we will see these 3 things. And this triangular form is the one that we are going to see in this section. Now before we go to the form itself and its existence, all those issues, we are going to need something called invariant subspace. So let's see that definition first. Let W be a subspace of V. Okay, so that means V is a vector space, and let T be a linear operator on V, coming from the operator algebra AV. We say that W is invariant under T if the image of W under T, that is WT, we are writing the image like this, but if you follow that other, the more usual way of writing functions, then the image will look like this, where you write the function first followed by the input within parentheses. We are, however, you already know, we write the input first followed by the function. And we also do not use parentheses unless there is some chance of confusion. So this is the image of W under T. If this image is a subset of W, then we say that W is invariant under T in the sense that applying T to W will not get us outside of W. I mean, any element, any vector in W, after all, is a vector in V. So, without any restriction on that vector, if we apply T, then the result will in general be a vector in V. But if that fails to go outside of W, in other words, if you have this containment, then we say that W is invariant under T. See, invariance doesn't mean that WT has to be equal to W. No, it only has to be inside W. Now the next lemma says something about invariant subspaces. So let's see what this one is. Lemma 641. Let W, which is a subspace of V, be invariant under some operator T on V. Then T induces an operator T bar on the quotient space of V by W. That means using T, one can get an operator T bar, which is a linear transformation from V slash W to itself. In fact, it's defined by this. You take any element in this quotient. In the quotient space, the elements are what? Cosets of W in V. So an element looks like this, where this V is coming from V. The T bar image of this is just the T image of V plus W. Okay, so the claim is that this is a linear operator on V slash W on the quotient space. And that's not all. There is something else also. If T satisfies a polynomial Qx in the polynomial ring Fx, a polynomial Qx over F, then so does T bar. T bar then also satisfies that same polynomial. And finally, if T1 of x and T of x are the minimal polynomials of the operators T bar and T respectively, then P1x divides Px. Okay, so these are the claims in this lemma. Now we are going to, I hope I have got the order correct. If P1x is the minimal, yeah. Now we are going to prove this. Now before we do anything else with T bar, the first thing we have to prove is that T bar is a well-defined function. Operator respecting addition, scalar multiplication, those things come afterwards. First comes the fact that it's a well-defined function. If it is not well-defined, if it is not even a function, then of course it cannot be operator. So we have to show that first. One thing we can immediately notice is this. Because T is an operator on V, so T maps V into itself. And that is why this V, small v, which is coming from capital V, will be mapped by T onto some element in capital V again. That means this Vt is again in V. And that is why this coset is again in V/W. So we know immediately at least one thing, that whatever the input is, this output is again there. However, that alone doesn't tell us that T bar is well defined. We also have to show that each input has a unique output. That fact also needs to be taken care of. So this is how we are going to show well-definedness. Let V1 plus W and V2 plus W belong to the quotient space such that they are the same thing. We then have to, that is, you have the two inputs which are equal. You then have to prove that the corresponding outputs are also equal. And you know that here it's a non-trivial issue because a single coset usually has multiple representations. This V1 may not be equal to V2. In spite of that, you may have the cosets equal. And this happens precisely when the difference V1 minus V2 is an element in W. Okay, so that's how we are going to start from this condition. Then V1 minus V2 belongs to W. And now immediately comes the to our rescue the condition that W is invariant under T. Since W is invariant under T, so if I apply T to this difference, the result will belong to W. That is, this will be an element in W. But T is a linear transformation after all, so this one is equal to V1T minus V2T. Just like equality of these two cosets implies this, the reverse implication is also true. If you have this, then you have this as well. And that's what we need now. So this minus this belongs to W, and that is going to imply that V1T plus W is equal to V2T plus W. but V1t plus W is the T bar image of V1 plus W. That is this. And similarly, this is the T bar image of V2 plus W. So equal inputs implies equal outputs. Hence, T bar is well defined. Okay, fine. So we have shown that the function at least is a legitimate function. It's a well defined function. Next, we have to show that T bar is a linear operator. That is, T bar respects addition and scalar multiplication. So let us take two vectors. Say, what shall we take? Let me just take U plus W and V plus W this time in our quotient space, and let alpha be any scalar from the underlying field. Then we will go through two calculations. One of them is we take the sum of these two vectors and on that we apply T bar and see what we get. So by the definition of addition in this space, this is U plus V plus W. And on this coset we are going to apply T bar. By the definition of T bar, this is U plus V T plus W. When you go through this kind of abstract calculations, it's very easy to make mistakes which ultimately lead you to write something which is completely meaningless. The more you write T bar, there is a tendency to write W bar suddenly. But then a few lines down, you will forget what W bar is. In fact, W bar has no meaning, but then you will get confused. So that's why always while going through such calculations, you mentally say these things, okay, in this step we are doing this. That's why it is like this. And always go slow. Now T is a linear transformation on V and it respects addition. So we have ut plus vt. And use as many parentheses, as many brackets as you want to make it more clear. Next, I can write one more line here. By the definition of addition in this space, this thing is equal to ut plus w plus vt plus w. And that is equal to u plus w t bar plus v plus w t bar. So we have shown that t bar respects addition. And next we are going to take the scalar multiple of alpha and u plus w, and on that we are going to apply t bar. Okay, so by the definition again, by that what shall we do here? We are looking at the product of a vector and a scalar. So what is the definition of scalar multiplication in this space? This is equal to, by definition, alpha u plus w, where alpha u follows the definition of scalar multiplication in the space V. Okay, I do not see V here, but in the space capital V. Now by the definition of t bar, we have to apply t on alpha u and then plus w. Because T respects scalar multiplication in V, so this becomes alpha times ut plus w. Then in the next step, you again use the definition of scalar multiplication in the quotient space. That gives you alpha times ut plus w. And this thing is nothing but u plus w t bar. If it still looks somewhat confusing, in order to emphasize the fact that alpha is outside of this process, you can use further brackets. So we have shown that t bar also respects scalar multiplication, and that is why t bar is a legitimate linear operator on v slash w. That is, it belongs to the algebra of operators on v slash w. Okay, so the first claim of our result has been proved. And then, that polynomial thing comes next. It is given that T satisfies the polynomial Qx. We have to prove that T bar also satisfies that same polynomial. Now this one needs more care. Let us first of all write an expression for the polynomial Qx. Let Qx be alpha naught plus alpha 1x plus alpha 2x square plus alpha 3x cube. I am writing so many terms, you will realize why. Alpha m x to the power n, where of course it's understood that these alpha i's are all coming from the field capital F. Okay. Now, first of all, we are going to make a claim. We claim that for any integer k greater than or equal to 0, any non-negative integer k, the kth power of the operator t bar is equal to t to the power k bar. Okay. We now need to prove this claim. Let us carefully see what this claim becomes when k is 0. In fact, we are going to apply induction on k. When k is 0, t bar to the power k, by the definition of integral powers, here actually you do not have to do anything. This is going to be by definition the identity element, the unit element. But where? The unit element in the algebra, in this algebra. In order to denote that fact, I have written one suffix v slash w to indicate the fact that this is the identity operator on this space. Okay. Also, now what happens to this though? This one is the identity operator, again just like that, the identity operator on V, but bar. Now we don't immediately know what this thing is. So let's see what it is by calculating its effect on any element in V slash W. Note one thing carefully, do not forget what this bar is, okay. For every operator T on V, there is a T bar. that we have defined in the statement of this lemma. Just like that, for the operator 1v, we have a 1v bar. And 1v bar is an operator on this space, v slash w. So we take any element in v slash w and see what we are going to get if we apply this operator on that element. For any element you can take again u plus w, say, in v slash w, we see that when we apply 1v bar on this element, by the definition of bar operator, we have to apply 1v on u and then write plus w. But 1v is the identity operator on v, and this u is a vector in v. So applying this on u gives you again u back. So you get u plus w. And this clearly shows that this thing is actually nothing but the identity operator on what? On this space. So it is actually equal to this itself. Thus, our claim is true when k is equal to 0. Now we are going to make the induction hypothesis. We are going to write it. Suppose t bar to the power k is equal to t to the power k whole bar for some non-negative integer k, some arbitrary but fixed non-negative integer k, and this is our induction hypothesis. Now we want to prove this claim for k plus 1. We now show this. Okay, and for that again let us take an element u plus w, our test vector. For any u plus w in v slash w we have. So what we are going to do, let us apply this on u plus w and see what we get. I think the calculation, if I write it centrally, it will look better. U plus w, on that I am applying t bar to the power k plus 1. What shall I get? The text, of course, doesn't have these details, and that's understandable because this kind of details, if someone wants to write a book with this kind of details, it will be prohibitively long. Some things we are supposed to do on our own. Everything the author cannot do for us. Okay. Now, by the definition of integral power, actually you can write this power in two of the possible ways. Okay, in two possible ways you can write. You can either write this as t bar times t bar to the power k, or t bar to the power k times t bar. So the second one we are going to write here. So we first apply t bar to the power k, and on the result we then apply t bar. Also, never forget that this kind of powers, alright, this kind of powers actually mean composition, because what is the multiplication in this algebra? That is function composition after all. Do not forget that. Now, by our induction hypothesis, this is equal to this. Okay, shall I run into some kind of problem if I first apply t bar to the power k? I guess we will see. Okay. So this becomes t to the power k bar, and on that we apply t bar. Alright, no, it's okay. Now t to the power k after all is an operator on V, and we are looking at its bar version. So by the definition of bar operator, we have to apply t to the power k on U and then write W. On this we apply t bar. Yes. So again, by the definition of t bar, we apply t on this and then write plus W. So this becomes this. And again, by the definition of bar operator, this is nothing but t to the power k plus 1 bar. Because the effect of both these operators on an arbitrary element are the same, so they are equal. Hence, okay, so our claim has been proved by induction. You need not write that. Okay, if you want, you can write in your notes, or if you are maintaining a note, there you can write nicely. Hence, our claim is established by induction. Fine, but this is of course not where we stop. We still have to show that t bar satisfies the polynomial qx, which is why we are doing all these things. Now, we straight away see what qt bar is. We have our polynomial, so we can write alpha naught 1. But what is this 1? This 1 is the identity operator on v slash w, plus, perhaps I should write on this side, plus alpha 1 t bar to the power 1. Actually, it's there, but there is no need to write separately. Alpha 2 t bar square plus alpha 3 t bar cube, and like that it goes, and finally we have alpha m t bar to the power n. Alright. Now here we can immediately use our thing that we have just now proved and write this is equal to, now in the first term we can do something. I mean, if you want, you can write this as 1v bar. This is in fact our induction, well, not hypothesis, but the basis of our induction for this result. And then you have alpha 1, well, this is just simply t bar plus alpha 2 times, here you can write t square bar plus similarly alpha 3 t cube bar plus alpha m t to the power m bar. However, it's not exactly clear what you should write after this. And when such things become somewhat difficult to see, again you take a vector from your underlying space and apply this entire thing on that vector. For any u plus w belonging to v slash w, we have, so on this now we are going to apply q t bar. So let's keep the vector separately and let's write this entire expression. Alpha naught 1v bar plus alpha 1 t bar. We cannot write everything here itself, of course. Plus alpha 2 t square bar plus alpha 3 t cube bar plus alpha m t to the power m bar. Now by the definition, okay. Now what is this plus and this scalar multiplication? These are operations in what? In this algebra. And by the definition of these operations, this entire thing is equal to alpha naught times u plus w 1v bar plus alpha 1 times u plus w t bar plus alpha 2 times u plus w t square bar plus alpha 3 times u plus w t cube bar, and like that finally alpha m times u plus w t to the power m bar. These extra square brackets emphasize the fact that we have written the scalars outside. Okay, so now we can just simply apply the, well, here writing 1 v slash w like this doesn't really serve any purpose because you get back this itself. That's because, you are applying the identity operator of the space v slash w on a vector, you are going to get back that vector. So here we do not get anything that interesting. And what about this? This is alpha 1 times, you see, now just you have to use the definitions of bar operators, bar versions of the operators. So this is ut plus w plus, what about this? Alpha 2 ut square plus w plus alpha 3 ut cube plus w and finally plus alpha m u t to the power m plus w. Okay. Now, if in place of this, all these things, I write this. Let me just go slowly. First I write alpha naught u plus w. Does it make sense? Yes. Because that's the definition of scalar multiplication in the space V slash W. So let me first write the terms accordingly. Alpha 1 times ut plus W. Okay, note carefully that I have used parentheses here to emphasize the fact that I am multiplying the vector ut by the scalar alpha 1. So I do not carelessly write alpha 1 ut without any brackets or anything. That at that point things have become confusing. But there are other terms also. Similarly, you have alpha 2 times ut square plus w plus alpha 3 times ut cube plus w plus finally alpha m times u t to the power m plus w. Equal to. Okay, now what shall we do? The first term, let me just keep it like that. From the second term onwards, let me write like this. U alpha 1 t plus w. Now what is this? We had alpha 1 ut, suddenly I am writing u alpha 1 t. It's because in the algebra AV, you take any element in AV, say you take t, and you take a scalar. There is a scalar multiplication because this being an algebra is after all also a vector space. Now you recall the definition of alpha 1 t. If you apply alpha 1 t on a vector coming from V, then by definition that is alpha 1 times ut. That's why we are able to write like that. Plus, the next term is here of course. So similarly, this is u alpha 2 t square plus w plus u alpha 3 t cube plus w plus, and finally you have u alpha m t to the power m plus w. Okay. Are we almost there, or do we need to do more calculations? After this, yeah, I have also got a little confused. What should I write after this? Do I have it here? Yeah, oh, okay, yes, I remember. You see, now the things that you are looking at in this sum, the terms of this final sum, what are these? These are after all cosets of W, right? And we know how to add cosets. So, according to the definition of coset addition, you are going to get this. U alpha 1 t plus u alpha 2 t square plus u alpha 3 t cube plus u alpha m t to the power m plus w. So this is a single coset. All right. So now you can forget about W. I mean, keep writing W outside, but all our concentration now is on this sum. Now, can I not write this entire sum like this? U alpha naught 1, well, what type of 1? 1V plus alpha 1 t plus alpha 2 t square plus alpha 3 t cube plus alpha n t to the power n plus w. You do understand what we have done here. This entire thing that you see within the parenthesis is an operator. An operator where? An operator on V. That means this thing that you are looking at here is an element in A of V. And by the definition of addition and scalar multiplication, well, we do not need scalar multiplication here. Addition is enough because we just have the terms here whose sum we are looking at. Now, applying this sum on U means applying the individual terms on U and taking their sum. That is the definition of addition in this algebra. So that's why we are able to write like this. Now, if you look carefully at that sum, that is in fact nothing but what? Isn't it Q of t? Because you have your polynomial Q like this, right? So you replace x with t, and here you write the identity operator on V. Okay, so that way you have this, but of course along with that you have W. Now it is given that T satisfies Q. That means this Qt becomes the zero operator on V, which we write simply as 0. That when you apply on any vector from V, you get the zero vector from V, capital V. Do you see the difference between this 0 and this 0? This is the zero operator on the space V, and this is the zero element, zero vector in the space V. And this of course is simply W. So you see what we have done. So on U plus W, we have applied the operator Qt bar. You remember, this is how we started our calculation. And we have got W, which is the zero element of the space V slash W. Hence, since this is any vector in V slash W, so this must be the zero operator because it takes every vector onto the zero vector. That is, Qt bar is equal to 0. So just like T satisfies Q, T bar also satisfies Q. Okay, so the second claim has also been proved. And now finally the third claim. What is the third claim? The third claim says that P1x is the minimal polynomial of T bar and Px is the minimal polynomial of T. Since Px is the minimal polynomial of T over F, T satisfies P, or in other words, P of T is equal to 0. Okay, being the minimal polynomials does not mean just that. It means that T satisfies it and it's the non-zero polynomial having least possible degree. But anyway, we only need this fact. Then, by what we have proved just now, T bar is also equal to 0. So that means T becomes an annihilating polynomial for the operator T bar. That means it is some polynomial which T bar satisfies. But T bar also has its own minimal polynomial P1 of x, which it satisfies, and which by definition is the annihilating polynomial having least possible degree. And when this happens, then we know from ring theory that P1 has to divide P. The minimal polynomial divides any annihilating polynomial due to the least nature of its degree. Hence, P1x divides Px, and that completes the proof. Now after this, of course, the actual thing starts, which we won't see today, but we will in the next video on linear algebra, next Friday, we are going to see this result. This next result is going to state this, that if T is a linear operator on V and all the characteristic roots of T are in the underlying field F, then there exists a basis for V in which the matrix of T is triangular, and that's how we get our triangular form. Triangular matrices we have already in fact got the definition in one of the exercises in the previous section. But anyway, we are going to discuss a little bit about the form triangular matrices before we state this result, and then we will state and prove this result. But anyway, that's just it for tonight. So see you in the next upload. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.